Welcome to this explainer. Today we're embarking on a journey into a vast, entirely invisible ecosystem. It's a landscape, but not one made of flora and fauna. No, it's built of mathematics and staggering amounts of data. It is the fascinating and sometimes perplexing world of artificial intelligence. We interact with it every single day, right? We marvel at its fluency, its breadth of knowledge, and its seemingly boundless creativity. Yet, just beneath the surface of this digital intelligence lies a beautiful, structured simplicity. So, here's the real question. How exactly does a machine that doesn't think sound so remarkably human? It's the elephant in the room, isn't it? Whenever we type a prompt and watch a perfectly crafted paragraph just materialize right before our eyes, it feels real. The illusion of a conversational, thinking mind is incredibly powerful. But as we'll see today, the reality of what's actually happening under the hood is perhaps even more awe-inspiring than the illusion itself. Right, let's dive into part one, the illusion of thought. To truly understand this digital ecosystem, we first need to strip away the magic and completely leave behind the myth of a conscious, reasoning entity. If we're going to grasp the reality of this landscape, we have to look at the foundational mechanism driving the whole thing. We are not dealing with a mind here. We are dealing with a magnificent, highly tuned prediction engine. The secret to this entire system boils down to one remarkably simple mechanism: next token prediction. It sounds almost too simple to be the engine of such vast capability, doesn't it? But think of it like a very observant local barista down in Melbourne. After a few weeks, that barista starts to anticipate your coffee order right after hearing your first few words. They haven't peered into your soul. They've simply learned your patterns so well that your next move becomes statistically highly likely. A language model operates in the exact same spirit, except instead of coffee orders, it's learning the patterns across enormous, sweeping oceans of text. Moving on to our second section, from words to numbers. Now, before a machine can actually make these astonishingly accurate predictions, it first has to translate our world into its own. We humans, we speak in messy, emotional, deeply contextual language, but a machine, it can't calculate meaning directly. To navigate this landscape, it literally has to convert our words into a mathematical reality it can compute. There is a stark, fundamental divide between human and machine. When you and I use words, they are anchored in experience, emotion, and truth. But the machine, it processes language as statistical regularities and plausible continuations. It doesn't know what is true in the human sense. It only knows what is mathematically most likely to be said next. And honestly, this is precisely why a model can sometimes generate information that sounds incredibly confident, yet is entirely fabricated. It's optimizing for plausibility, not verifying facts. To process all of this text, the model doesn't just swallow sentences whole. Instead, it chops raw text into smaller chunks called tokens. Think of these tokens as the foundational Lego bricks of language processing. A single token might be a whole word, maybe just part of a word, or even just a punctuation mark. See, if the model only used giant, fixed blocks of full words, it would totally stumble over rare words or strange phrasing. But by breaking language down into these smaller, flexible Lego bricks, the system can build a nearly infinite variety of linguistic shapes. Which brings us to section 3, the geometry of context. Okay, so once we have our tokens, they are transformed into numbers. But these aren't just random digits. Imagine a colossal, multi-dimensional stadium map. Every single token is assigned a very specific seat on this map. And words that share similar meanings or behave similarly in language, they actually cluster together in distinct neighborhoods. So cat and puppy sit right near one another, while banana resides in an entirely different section altogether. Language itself becomes a beautifully navigable geometry. However, a word sitting all alone on that map doesn't tell us the whole story. Context changes absolutely everything. Take the word bank, for example. Are we talking about the site of a river or a financial institution? In this system, a token is just like a chess piece. A knight in isolation is really just a carved wooden shape. But place it on the board and its power, its actual meaning, is forged entirely by its relationship to all the surrounding pieces. The model doesn't ask, what is this word? It asks, what does this word mean exactly here, right now? And here's the absolutely crucial point. The model doesn't confidently know a single absolute answer. When faced with the phrase peanut butter and, the model mathematically ranks the most likely continuations. Maybe jelly's at 70%, jam is at 20%, and banana sits at 10%. It acts remarkably like a probabilistic weather forecast. A meteorologist doesn't declare it will absolutely 100% rain. They balance the likelihoods. The AI does the same. It explores a distribution of possibilities and just gives us the most plausible path forward. Let's explore Section 4, Learning Through Correction. So how exactly does the machine acquire this remarkable intuition for probability? Well, it enters an evolutionary phase, which we call the training process. The system has to learn, through endless massive trial and error, how to make these incredibly accurate guesses. Good prediction reduces surprise. This simple, elegant phrase is the actual beating heart of the model's learning engine. The system observes some text, guesses the next token, and then checks its answer. If it's wrong, it makes a microscopic adjustment to its internal mathematical dials so that it will be just a little bit less surprised the next time around. Picture a child trying to learn a rhythm by clapping along to a favorite song. At first, their timing is completely off. But with each beat, they listen, they adjust, and gradually those claps fall perfectly in sync with the music. Through massive, mind-boggling exposure to data, the model begins to understand language at multiple scales simultaneously. Imagine feeding the system countless transcripts from an Australian customer service center. It doesn't memorize the exact conversations. Instead, those repeated corrections build up a sort of internal pressure system. It naturally absorbs the local grammar, then the mid-range flow of a polite refund request, and eventually the larger narrative style of a formal business interaction. It literally learns the shape of the terrain simply by walking it millions and millions of times. Now, for our final section, Part 5, the emergence of complexity. Up to now, we've observed the microscopic elements, the tokens, the numbers, the tiny internal adjustments. Now we finally get to witness how these localized, microscopic predictions scale all the way up into sprawling, coherent structures of thought. And this brilliantly illustrates the complete migration of a single thought through the entire system. Look at the loop. We start with raw text, we break it into those Lego brick tokens, we convert those into mathematical numbers on our giant stadium map, we evaluate their context like pieces on a chessboard, and finally we generate those probabilistic predictions. This looping mechanism is, at its core, remarkably simple. It is the vast scale and the endless, relentless repetition of this loop that produces the profound complexity we see before us. You see, a single token prediction is pretty meaningless on its own. It's simply a single tile. But when you lay hundreds or thousands of these tiles together, step by step, an intricate, gorgeous mosaic emerges. The model has learned the deeper relationships of language, much like learning to play music by ear, rather than memorizing a single sheet of notes. This is what enables it to handle entirely new melodies, new prompts it has never, ever seen before, generalizing its rules to paint a complete and coherent picture. Which leads us to a truly profound realization. To quote, "A large language model is not a mind pretending to be a machine. It is a machine that has learned the structure of language well enough to behave in surprisingly mind-like ways." We have to shift our lens from viewing artificial intelligence as some sort of unexplainable magic to recognizing it for what it truly is, an elegant, majestic pattern engine beautifully shaped by the very contours of human language. So you are no longer just an observer of this technology. You can now actually see the mechanism beneath the behavior. You know that it's ranking probabilities, it's reading context, and it's constantly reducing surprise. So as you step back out into our increasingly digital world, empowered with this brand new understanding, now that you know exactly where the mystery lives, what will you ask it next?